Hi all, this video is for preparing the quiz 1. Quiz 1 will be released on Tuesday on 8:30 a.m. and it'll be open until Wednesday 11:59 p.m. So technically it will be open for 2 days. And there will be no class, and then the quiz will be delivered via Canvas, so please take the quiz via online. Quiz duration is technically unlimited. I will set it as like several hours, for example, 8 hour-ish. But I believe like most of you could finish it in around 30 minutes or maybe at most in an hour. And you will have 3 chances to make attempt to solve the quiz, and I will take the highest score. So please use all 3 chances if you cannot make the 100% score from it. So I wish you, all of you, get like the 100% score from quiz 1. Additionally, the quiz taking policy is allowing open material use. That is, you can refer to any contents in our course website, including lecture, tutorial, slides, and videos. And also, we allow you refer to your JOS Lab 1 and Lab 2 code, and also for referring to the textbook. But I believe that referring to the textbook is not that required. But please do not communicate with the other students during taking the quiz. And another thing, you can ask questions for the quiz, but ask question only if there is a factual error or you cannot understand what question is asking. What that means is that like please do not ask myself or TAs about like is this answer correct or not. So we will not giving the answer for that. But if there's some of the factual error in the questions, I believe like there will be not that much. But if that is the case, then please ping us over Discord about that. There will be 11 questions, and it's 1 point each. And we will cover the topics that we have learned until last week. Starting from BIOS booting CPU and real mode segmentation, it will also include protected mode segmentation and paging, virtual address translation, and virtual memory layout. And it will also cover JOS memory management and JOS Lab 1, especially for Lab Tutorial 1 and 2. And for the first part of the JOS Lab 2 is included, so please refer to these listings when you refer to the materials to study about the questions. From now on, I will go over sample quiz questions, and the real quiz will not be much different from these ones. So please walk through those questions thoroughly, then you can solve the questions as the real quiz questions easily. Let's start with the first question, real mode segmentation. In JOS Lab 1, the first instruction that the QEMU emulator runs in is from BIOS, and it is stored at F000:FFF0. The instruction is this one, with the long jump. Then the question is, what is the address of the next instruction? So it will do long jump, so the question is that like what kind of the address? This segment and offset pair will be translated to. That's what question is asking, which the CPU will run after this instruction, right? Yeah. So to calculate the real mode segmentation, if you cannot do that, please refer to these links. So that these links are also available during taking the quiz. So please go to these materials and then study about that. And as a shortcut, I will provide some solutions. So real mode segmentation, how we can calculate the address is like take the segment register and then multiply that by 16 and then add offset. And let's do that with this address pair. So segment register value is 0xF000, and then we will multiply this by 16. So in hexadecimal numbers, hexadecimal is about the 16, right? So multiplying 16 to a number means that adding 0 at the end. So you can think it as in decimal numbers, if you multiply it by 10, then we just add 1 0, right? So that's the same thing. Multiply by 16 is adding 1 0 at the end in the hexadecimal number, and then we need to add the offset. So F0000, and then add E05B, so we can easily add those because 4 digits are 0. So the answer is FE05B. Real mode segmentation in A20. In the real mode of x86 with A20 disabled, which address does the following segment offset combination points to? So now we know how to calculate the segment offset based address. But in this case, the question notes that like the A20 is disabled. What that means? So A20 disabled means that we need to ignore the address bit at 20, and then that means we need to regard that as 0. Then this exists because like there was an error that like we don't have a main memory more than 1 megabyte. So there could be this kind of the segment offset pair could point to the more than 1 megabyte region. But in that case, in that error, there's no memory out there. So just ignore it. Then we can use that to point to the low address. But in these days, we don't need that because we have a much bigger memory than 1 megabyte. So right now in JOS, we enable A20. So this case is with the A20 disabled, but if the question asks that like the A20 is enabled, then you should not ignore the address bit at 20. After knowing this, let's try to calculate the address. So the segment is F800, so we will multiply that by 16 and then add the offset F100. And you don't need to do this kind of calculation with the paper and pencil. So we are computer scientists. We have this kind of computers interpreters, so we can just run it and put the segment address, multiply by 16, and add the offset, and then transform that as an hexadecimal number. Then you can easily get the answer like this. And after that, we need to identify what is the address bit at 20. So let's represent the resulting number in bits. And then that means, so each digit of the hexadecimal number can easily be translated into like 4-digit binary number. So we will translate 0 to 4 zeros, 0 to 4 zeros, 1 as 0001, 7 as 0111, 0 as 40, and then this 1 as a 0001. And then in computers, all the indices are starting from 0. So 4-bit, 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 4-bit. These are 20 bits, but starting from 0 to 19th. So the address bit at 20 is this one. And then you can easily see that this one indicates that this address is over 1 megabyte. And then with A20 disabled, we will ignore this bit. So this is the 20th bit. And then we will ignore that. And then exactly this one. And we will regard that as a 0. So the answer is this will become 0. And then removing all heading 0 at the heading, then we will get the 0x7100 as the resulting address. But please make sure that the question asks about like A20 disabled, then you need to ignore this bit. But if the question states that the A20 is enabled, then you should use the address as is. Next question is about JOS Bootloader. Which of the following is not a job that the JOS Bootloader does? So I will show you that what kind of the selections are available right next to this slide. But whenever you encounter this kind of questions, try to find like the slide that directly describes about like what JOS Bootloader does. And then from this kind of slide, you will see that starting from BIOS and then BIOS load the boot sector. These are the things that the BIOS will do. And then bootloader will do enable A20, enable protected mode, and then read kernel ELF. And then let's take a look at the selection. So does the JOS bootloader read the JOS kernel from the disk? Yes, it is. Does it enable protected mode? Yes, it is. Does it enable A20? Yes, it is. Load the JOS kernel to the physical address space. Yes, it is, because we are not enabling virtual memory at all, so it will be uploaded to the physical address. And then the answer is enable virtual addressing. So in the bootloader, we do not enable virtual addressing at all. Then as a side question, when does the JOS enable the virtual memory paging? So that's in the kern entry.s. So under the directory kern means that it's in JOS kernel, not the bootloader. And then in the assembly code, we will see that it's turning on the paging, getting the CR3 value to EAX, and then protected enabled paging and write protected, and then set those flags and then put it back to CR0. So after running this instruction, the paging will be enabled. So in short, enabling virtual memory, the paging, is the job of the JOS kernel, not about the JOS bootloader. Question 4 about the JOS bootloader. The JOS bootloader loads the JOS kernel at the physical address at 100,000,1 MB. And then how does JOS decide the address, this one, to load the kernel? And for this part, if you follow the JOS bootloader source code, then you will see that like the boot.c in there, then you will see that how JOS loads the kernel. And then how we read the segment is that we will put the loaded data into physical address of the something, and then that kind of thing is actually described in our lab tutorial description. So if you refer to the course website about the lab 1 part, and then you will see that this kind of the descriptions is there, and then the kernel is written in the ELF, executable and linkable format, and then that format has a program headers to decide how to load sections. And then in the program header of the kernel, you will see that load to 1 MB as an address. Then that's how JOS decide the address 100,000 to load the kernel. So it's not about the arbitrary address. In compiling the kernel, JOS defines this address to be loaded to the kernel. So JOS bootloader knows this address from the ELF header. Next is x86 program stack. Suppose you have the following code snippet in your JOS. So it's about reading EBP, and then you need to get the EBP, and then get EIP, and then printing the result out of it. So I removed the argument and then other parts, but just focusing on the EBP and EIP. So you can regard this as like the simpler version of the JOS Lab 1 exercise 10, 11, 12. Yeah. And then what kind of the code you need to assign in this part? So the selection will be showing some of the example code. And then you can get the answer for this kind of question from the tutorial slides. And then it will show that to print EBP and EIP correctly, then what we should put it here. So that's the goal of like this question. So please study through the tutorial, lab tutorial, and also please refer to your code for what kind of snippet you have coded in there. And question 6 is about the protected mode segmentation. So we have gone through the real mode segmentation in question 1 and 2. Then now it's about the protected mode. We have the following global descriptor table, and it is loaded via LGDT, and the CPU is enabled with the protected mode. So that means we should translate segment offset pair using this as a global descriptor table. And the question is that, in this case, what memory address is accessed by the following segment offset? So you need to choose like the address for each A and B and C, yeah. And then and also for the if the access is invalid, then you should not choose the address but you must choose the invalid address. And then let's go over like each item. So A, segment selector is 0x10. So it will select this row, and then we need to get the base address first. So the base address is this one, and then our offset is 1010. And then if we calculate the resulting address, then that will be 11122, 3 plus 1 is 4, and 010. And then to check if this address is inside the limit or not, we need to take a look at the G bit. Even if the offset is bigger than the limit, if the G bit is 1, then we need to multiply limit by 4096, which is a hexadecimal 1000. So that's actually over the limit. This is not 400000. This should be 100000. Yeah, but it doesn't matter. Yeah, so that if the G bit is 1, then it will be the 1 mega, so which will be much bigger than current offset. So this address is valid and allowed to be accessed by the current selector 10 and 10. Then address B, segment selector is 0x8, and then offset is 1010. Then from the segment selector 8, so we can get the base address 44556000. And then G bit is 0. That means the limit is this one. And then our current offset is bigger than the limit. Then that's an invalid access. And then, so the first one, the answer is this one. Second one, the answer is invalid access. And then the third one. So for the first and second one, we can easily see that like this 10 means the 16, and then 8 is 8. So if we take the last two bits of the segment selector will store the running permission, and then we will see that all the last two bits are 0. But in this case, you will see that the last two bits are 3. Yeah, that's the different case. But in such a case, so even if the 0x13, that is the segment selector, we need to ignore last two bits, so we will ignore 3. So it should be 0x10. So we will refer to this global descriptor. And then let's calculate let's try to look at whether we can access this or not. And then the current privilege level is stored at the last two bits. Yeah, last two bits of the segment register. So for example, if the CS register value is 8, then that's 10000. So last two bits are 0. So it's about the kernel mode. So 0 means kernel, and then 3 means user. 0x10, 10000, 2 zeros at the end, kernel. But 0x13, 10011, last two bits are 3, so that's for the user mode. And then 0xb, which is 11, is 1011. So last two digits are 3, so that's our user mode. And then in that case, we need to refer to whether the DPL allows that level or not. So if the level is user, but the DPL is 0, then we cannot access. And then let's take a look at this case. So we have a segment selector 0x13, and then if we take the last 3 bits, so the last 2 bits, to do that, you can just apply AND operation to number 3. Because number 3 is a 1, as a binary number, and then the result is 3, so that means our privilege level is 3. And then in the ring level, so ring 3 is for application, the user level, and then ring 0 is the kernel level. So ring 3 can never access memory for the ring 0. That's the ring protection level. And then let's take a look at the descriptor privilege level. So the descriptor privilege level for this descriptor is mentioned as a 0. That means the memory is kernel access only. But the currently learning permission level is 3, which is a user. So our permission level is, the number is higher, that means like the privilege is lower. Yeah. So we cannot access this, so that's an invalid address. So in solving this kind of questions, please don't get confused about like a protected mode segmentation is you should go through the global descriptor table, not about the multiplying 16 and the offset. And then after referring to the global descriptor table, you need to take the base address and then compare the limit and offset. But in comparing limit and offset, you need to take a look at the G bit. If that is 1, you need to multiply the limit by 1000 in hexadecimal and then 4096 in the decimal number. And then the last one, if the segment selector has a current privilege level different than 0, then you should check whether the descriptor privilege level is allowing that or not. So in case of C, we have a current privilege level as 3, but the descriptor has the privilege 0, so 3 cannot access 0, but 0 can access 3. So that's the important part. Question 7 is about the virtual memory. We have learned the 3 goals of the virtual memory: transparency, efficiency, and protection. And then the question is about which of the following describes the transparency goal. And then in the question selection, the answer selections, it will have some descriptions. And then you should choose the best description matches to the transparency goal. But if you are not sure about the transparency goal, you can refer to this slide directly describing about what is the transparency and then like how we can get that with the virtual memory. So the transparency is that the program, when it will be loaded, it does not have to care for like what kind of the memory layout in physical memory the system uses. So without virtual memory, we need to take care of like what kind of which part of the physical memory is being used by the one program, and then the other program need to be loaded totally different address. But by using the virtual memory, we can give the entirely empty address space to program 1, and then entirely empty address space to program 2, so that they can use the same address, while the same address will be totally different address in the physical memory at all. And then next question is about the virtual memory. We have learned the 3 goals of the virtual memory: transparency, efficiency, and protection. And which of the following describes the efficiency goal? And then you can also refer to the part of the slide that describes the efficiency. And then that mentions about the memory fragmentation problem. And what that is that suppose you have a program 1 loaded like this, but although adding up all the free space can accommodate all these 3, the program data, code, and stack part, but that there is no physical memory that is empty contiguously for 160 kilobyte, so we cannot load that. So here, we do not use 32 kilobyte, so 96 minus the 64 is a 32. And then if we move this part a little bit, then we can fit the code too. But we cannot easily move the program code because it requires we need to update all the pointers because the program is in running. Yeah, so we cannot easily do that. So in this case, we cannot load the program 2 because there is a fragmentation, even if all the free spaces is equal to bigger than the entire size of the program 2. So that was the problem of the efficiency. So you should choose the answer that is the most close to this kind of the phenomenon. And question 9 is about the virtual address translation. So let's do it step by step. We have the following page directory and page table. So this is page directory and this is page table. And then in the page directory, the presence of each flags means that the flag bit is 1. So for example, PTP, then we will regard the PTP as 1. PTP and PTW, then P and W are set as 1. And PUW, then these are set as 1, but if there's no flag mentioned, then you can regard that value is 0. This is page directory and page table. And then the CR3 register of the CPU points to the page directory address. So you can regard this page directory and table is the directory and table that you should use to translate this address. And then which physical address, the question is that which physical address that a virtual address, this one, will be translated to. So let's do that. So 8021567. So just write it, and then we will not translating the last 3 digits because we will manage the memory by page granularity, and then page size is 4 kilobyte, and then that's why we do not translate last 3 digits. So virtual page number is this one, and then offset is this one. And then after splitting that like this, what we need to do is we need to write this down as a 20 bits. And then 1, 4 digits, 0001, 2, 4 digits, 0010, 0, 0000, 8, 1000, 0, 0000. And then these are the 20 bits. And then we will use a lower 10 bits to access page table, and then higher 10 bits to access the page directory. So that's why I colored the lower 10 bits as a blue color, and then higher 10 bits as a red color. So we will use red numbers to index page directory, and then blue numbers to index page table. And then if you just translate this number as a hexadecimal, then so it's split in the middle. So 1, 2, 3, 4. These 4 digits are becoming this 0. And then these 4 digits, 0, 0, 1, 0. That's actually 2. So that's why we have 2. And then 0, 0. So these are 0, so ignore it. So the higher 10 bits, the page directory index is 0x20. And then lower index. So it's easy to calculate. The same number and then has 1 at the end. So the page table index is 0x21. And by using these two numbers, let's try to translate that. So page directory index is 0x20, so we need to choose this entry. And then its physical page number is 111. And then physical page number is 111, corresponding physical address. We need to add 3 zeros at the end. So that will refer to the page table at the physical address 111000. So after referring to this one, then we can find the corresponding page table. And then next is using page table index. So that's 0x21. So we will choose this one. And then it will be using 0x567 as a physical page number. And then physical page number is 567. And then our offset at here was 567. Page number plus offset, that's it. It's not plus, actually concatenating, because we do not translate the last 3 digits and then just paste it at the end. Yeah. So this is how you can get the answer for the address translating question. But please note here that I do not ask any kind of permissions or something, so you don't have to refer to the flags right now. Just translating the virtual physical number into page directory index, table index, and then refer to the directory and table to figure out the physical page number and giving the offset, then you can translate the address. And the next question is about the address translation too. So we have a following table, and then in this case, we need to translate this address, 8020333, different address. Then let's do the same thing. So 5 digit, 3 digits. Then virtual page number is this one. Offset, last 3 digits are this one. Then do the same thing. 20 bits, but here, so we have a same 0x20 for page directory index and page table index. And then we will use these two index to access page directory and table. We first access 0x20, so it will find the page table at 111000. So it will refer to this one. And then it will choose 0x20, and then that's 234 for the physical page number. So physical page number is 234, and then offset is 333. So the resulting address is 234333. So the example selections is something like these, and then the correct answer is this one. Then last question about the address translation. So in this case, it will ask for the permission, and then we have the following page directory and table, and then the question is that what is the memory permission applied to the virtual address A021212? And to do that, we need to go through the address translation first to see which entries are involved in, and then later we will check that they do have what kind of permissions are there. So the first thing is that cutting off the last 3 digits, then split it as a virtual page number and then offset. And then if we translate the virtual page number into page directory index and then table index, it will be something like this. And then we will choose 0x20, and then we will choose 0x21 because 111 is the physical page number, goes to the page table at here, and then we will use this index to choose this row. And then we will take a look at the permissions. So that we can easily get the address. So the physical address will be 567.212, but that is not the important question here. So the question is about what is the memory permission applied to the virtual address, this one. And then from the page directory entry, so we will see that the PTP and PTW are up. So there's no PTU. And then page table entry, PTP, PTU, PTW, these are all up. But because CPU will check the permission at the page directory entry first, and then it will also check the page permissions at the page table entry. So we need to take the set intersections of these flags, and then that will be the final page permissions. So if we take the set intersections of these flags, so there's no PTU, so we will only have a PTP and PTW. And then what is the meaning of that? So PTP is there, so that means this address is valid. And then PTW is there, so the address is readable and also writable. But there's no PTU, so this is only for ring 0, the kernel mode. It's not about the user mode or application. So the answer will be readable and writable, but inaccessible to the user, only for ring 0. So this is the end of the quiz 1 prep, but the actual quiz questions will be very similar to these kind of questions. So please take your time to go through the videos and then try to understand how you can solve each questions. And then you can also refer to this video while taking the quiz, and then that will be very helpful to you. All right, this is the end of the video, and I wish all of you can get a great score from quiz 1. Thank you.